Okay, before we begin our today's lecture, if you have any questions, please ask your questions. Any question in the previous lectures? Okay, if there are no questions, then last time, if you remember, we were discussing these design steps. And within the design steps, we were talking about the maximum number of bars that can be placed in a single layer and minimum number of bars that can be placed in a single layer. So minimum number of bars which can be placed in a single layer are, as per ACI code given in this table, up to 15 inch of width of the beam, at least two bars must be placed inside the beam. And when the beam width exceeds 15 inch, then up to 24 inch, 3 bars should be placed, at least 3 bars should be placed in the beam, regardless of how many bars are required. So these are the minimum number of bars required in one row, in one layer. The next requirement according to the ACI code is that where beam reinforcement is placed in 2 or more layers, the clear distance between layers must not be less than the greatest of 1.5 inch, 1.5 dB, and 4/3 D aggregate. D aggregate means the maximum size of the aggregate. And the bars in the upper layer should be placed directly above those in the bottom layer. So sometimes you may come across a situation where the number of bars placed in one layer may not be sufficient. So second layer of bars will be placed, and if second layer of bar is to be placed, then there are 2 requirements as per ACI code. One is that the distance between the 2 layers shall be at least 1.5 inch clear distance, are equal to 1.5 diameter of the bar, or 4/3, which means 1.75 the diameter of the maximum size of the quartz aggregate. So let's say the maximum size of the quartz aggregate is 3/4 inch. 4/3 into 3/4 will give you 1 inch. Let's say the diameter of the bar is 1 inch, so 1.5 multiplied by 1 inch will be 1 inch, and 1.5 inch is also a requirement. There are 3 requirements. The greatest of 1.5 inch, 1.5 dB, and 4/3. So the greatest of these 3 shall be taken, and 2 layers shall be placed according to the greatest of these 3 requirements. Okay. So normally we place this by it is spacing up 1.5 inch. Okay. And the second requirement of the ACI code is that the bars in the upper layer should be placed exactly above those in the bottom layer. Exactly those in the bottom layer means that, for example, you need 4 plus 2 bars. So 1 bar should be placed here, another bar should be placed here. If 7 bars are required, then 4 bars will be placed here, 1 bar will be placed here, but a third bar cannot be placed neither in the middle of these 2 bars in the second layer, nor on one side and other side of the centroid. This is the centroid of this beam. So if you place 1 bar on one side of the centroid, then the area of steel on one side of the centroid will be less and the other will be more. So instead of 3 bars, we will place 4 bars, and we will round this up, and 4 bars will be placed like this. So all these placement requirements must be fulfilled, because these are the requirements of the ACI code. And these requirements are meant for easy pouring of concrete, because one of the main assumptions in the mechanics of reinforced concrete is that concrete should flow around all bars, and the flow of concrete is important because the basic assumption in the mechanics of reinforced concrete is that steel should make a perfect bond with concrete. Okay, this is another requirement, and according to this requirement, if bars are to be placed of different diameters in one layer, this is one layer, and if bars of different diameter are to be placed, then the bars shall be limited to 2 bar sizes, which means that, for example, if you want to place number 8 bar here, so number 6 bar can be placed inside this layer in this manner, but not less than number 6 bar, because if this bar is number 8 bar and this bar is number 5 bar, then the bars in a single layer are not limited to 2 bar sizes, because the difference is 3 bar sizes, 8, then we have 6, 7, 8, after 8 we have 7, number 7 bar, then number 6 bar, and then number 5 bar. So the difference will be not limited to 2 bar sizes, it will become 3 bar sizes. In one layer, this must be followed, okay, in one layer. But if bars are to be placed in the second layer, then it can be of any diameter of the bar. And there is another requirement that if bars are to be placed in the beam, the bars must be placed symmetrically. Symmetrical placement of the bars are as shown in this figure. There is centroid of the beam. So the area of steel on one side of the centroid and the other side of the centroid must be equal. Because if the area of steel on both sides are not equal, then the T, which was taken at the centroid of the beam section, will shift to either this side or this side. Okay, finally, we will, after placement of bars, we will check the flexure capacity from the actual D and actually placed amount of reinforcement. We know that phi m is equal to phi ASA phi D minus A by 2. Phi m is equal to phi ASA phi D minus A, and phi m must be greater than or equal to mu, where mu is the factored applied moment. So what we do is that initially we will assume some effective depth of the beam in order to calculate area of steel, but finally this effective depth must be checked. This is checked like this. If this is a beam, the cross section of a beam, the total depth of the beam is h. Let's say this is now. Let's say the beam depth is 18 inch. Initially, we will assume some effective depth of the beam because you do not know the area of steel in the beginning. So you know that effective depth is the distance from top of the beam to centroid of the reinforcement placed. And since we do not know what will be the area of steel after the beam is designed, and whether the area of steel will be placed in one layer or 2 layers or 3 layers. So we will not be in position to exactly calculate the effective depth. Okay. So in the beginning, what we will do is that we will assume some effective depth D based on our experience, let's say. So for example, in this case of 18-inch deep beam, we initially assume effective depth of 15.5 inch. When effective depth of 15.5 inch is assumed, then D is equal to H minus Y bar. H is 18 and Y bar is the distance from bottom to the centroidal distance, bottom of the beam to centroidal distance. So this is 18 minus 3.15, this will be 18 minus 2.2 inch. So initially Y bar will be 2.2 inch, okay? But after we place the bar, let's say we design the beam and the reinforcement finally calculated is such that 5 number 6 bars are to be placed inside the beam in this manner. 5 bars, 3 bars in one layer and second bar in another layer. So now we can exactly calculate effective depth. How? We can take a moment about the bottom of the beam, okay, for the whole area of 5 multiplied by, this is the number 6 bar, so 5 multiplied by 0.44, and let's say because we do not know the centroidal distance, so for this Y bar we will assume Y bar in the beginning, 5 into 0.44, which is the area of shield, into Y bar. So this will be 5 into 0.44 into Y bar, total moment about the bottom, and then the moment of this 3 bars separately and the moment of this 2 bars separately about the bottom of the bar. For 3 bars, this will be 3 into 0.44 into Y1. What is Y1? Y1 is known to us because from the bottom we know that the distance up to the the clear distance from the bottom of the beam to the stirrup, which is 3 by 8 inch, is 1.5 inch, at least 1.5 inch. Y1 is 1.5, which is the clear cover, plus 3 by 8 inch, which is the size of this stirrup. 3 by 8 plus half of this bar, which is now 6 by 8. So half of this 6 by 8 is 2.25 inch. So Y1 we can calculate. So similarly, Y2 can also be calculated, because we know this distance 1.5, then plus 3 by 8, plus bar diameter, which is 6 by 8, and then plus 1.5 inch, which is clear distance from the top of this bar to this distance, and then half of this bar, which is 6 by 8, half of 6 by 8. This comes out to be 4.5 inch. Now,
excuse me, sir.
Please.
Sir, what does 0.44 show?
0.44 is the area of steel of because the bar is number 6, so the area of steel is 0.44 square inch. Okay.
Okay, sir. Thank you.
So in this manner, y bar can be calculated. Y bar finally from this equation, because y1 and y2 are known to us, y bar comes out to 3.15 inch. So initially, the effector depth assumed was 15.5 inch, but now you can exactly calculate the effector depth after the placement of reinforcement. So this will be h minus y bar. This is 18 minus 3.15, 14.855 inch. Since the phi mn equation has the value, the phi mn equation contains the effector depth d. So if effector depth d decreases, it means phi mn will also decrease. In this case, the assumed effector depth was 15.5 inch, but the actual depth is 14.85 inch. So which means that finally phi mn of the beam may come out to be less than the phi mn calculated. Okay, so then we have to check this phi mn with the actual area of steel and actual d. And then based on the design, drawings of structural members are prepared showing the dimension of member and detail of reinforcement parts. So these are all steps of design. These steps will be further clarified in the examples which is coming next. This is an example. I would like that you write down at least the statement of this design example. This will be your first design example. So you better write down. These are just to simulate. In the beam, you can see some sandbags. These bags basically simulate the uniformly distributed load. How a uniformly distributed load is applied on a beam. This is a uniformly distributed load applied on a beam. The beam should be designed as per ACI 318-19. The dead load of the beam is the dead load excluding self weight of the beam, which means that this dead load does not include the self weight of the beam. Is 0.5 kip per foot. Live load on the beam is also 0.5 kip per foot. The beam center to center, center of the support to center of support length is 20 feet, and FC prime, which is the concrete used in this beam, specified shall be used in this beam, and the yield strength 40 KSI means that the yield strength of the reinforcing bars, which is to be used in the beam, shall have a strength of 40 KSI. Okay. Now you should pay attention to the design of this beam, because this is your first design problem. We will go in the design problem slowly so that you can understand different steps. If you have any question, you can just tell me your name and ask your question anytime. You can stop me and ask your question. Okay. You should also take a piece of paper and a pen and try to do calculations, okay, and participate in this design problem. Okay, the first step will always be to select some size of the beam. You know that in one of the slides in the previous lecture, I would show that slide once again. This is the slide. Initially, the depth of the beam. These are the ACI recommendations for the minimum depth of beams. Okay, and this is covered in ACI 9.3.1. ACI code recommends that in the beginning, the depth of the beam shall be estimated from these equations. Okay, you can see that for a simply supported case, the minimum depth of the beam shall be assumed equal to L by 16 inch. You should remember that these recommendations of the ACI code are meant to minimize deflection in the beam, in an indirect manner. So you can take a depth larger than this within reasonable limits, but not less than this. Okay, because if you take depth of the beam less than this, then there will be a possibility of excessive deflection. Okay, although the beam may not fail, but the beam may deflect excessively. So, which again is not a desirable situation. Okay, so L by 16 is the depth of the equation for the depth of the beam. We will use this L by 16 for the depth of the beam. This is 20 divided by 16. To convert this into inches, we will multiply this by 12. You can do this calculation yourself. So 15-inch total depth of the beam, at least 15 inches is required. But there is a note in the slide. I will show you the note again. There is a note at the end of the slide. This is the note. That for Fy other than 60 KSI, the expression in table shall be multiplied by 0.4 plus Fy divided by 100,000. So these equations are only for grade 6 steel. To convert these equations for steel other than 60 KSI, this expression shall be multiplied with these equations. So 0.4 plus 40,000 divided by 100,000, this will also become 0.4, 0.4 plus 0.4 will become 0.8. So the depth can be further reduced by 20%, or L by 16 can be multiplied by 0.8. Okay, so after this is 0.4 plus 40,000 divided by 100,000 is 0.4, 0.4 plus 0.4 is 0.8, 0.8 into 15 comes out to be 12 inch. I will say again that this is the minimum depth requirement of the code for depth of the beam. You can assume slightly larger depth in this, okay, but not, you cannot select a beam with the size less than this. Finally, we decide to select a beam with a depth of 18 inch. Okay, so why we do this? Because the size of the beam will be the selection of the size of the beam will depend on many things. Number one is the ACI code criteria, which I tried to explain to you right now. But there will be many other things from practical point of view. For example, the farm work availability. You know that reinforced concrete is prepared. The members of reinforced concrete are prepared at the site, and the farm work must be placed before the preparation of any member of reinforced concrete. Farm work, you know, farm work, okay? And farm work is not available of all sizes in a locality, okay? Or they are not always available, okay? So for example, if you want to prepare a beam, to make a beam of, let's say, 12 inch wide and 15 inch deep, you must have the information that whether this farm work is available in my locality or not. Because the farm work, if farm work is not available in an area, then it will become very difficult to prepare a fresh farm work for just one beam, because this will our final objective is to produce a beam which is economical as well as safe. So safety is ensured by our calculations, and the economy can be ensured taking into account the practical constraints. There are many practical constraints which must be known to us before deciding the size of the beam. For example, I would say a few things about the farm work now. I will share my experience with you about the farm work. The readily available sizes in the market for the beam are a 12-inch wide beam with a 18-inch deep beam. This is a readily available size. If you just go to the market, you will be able to find a farm work of this size. But if you want to have a size of, let's say, 12 by 13 inch or 12 by 15 inch or 12 by 14 inch, then you will have to struggle for this. The farm work may not be easily available. And finally, what you will do, you will use you will use those sizes which are available in the market. You will not be able to use the size that you have assumed in your calculation, because to prepare a new farm work for just one beam or for few beams, it will become uneconomical. So we have to use the available sizes. So we have to keep these things in mind while designing any member, be it a beam or column or slab. So, and this availability of the farm work is one of the main constraint in the design of reinforced concrete. So generally, the depth of 18 inch is readily available. Depth of 24 inch is also available. And if we slightly increase the depth of the beam, you know that phi mn is equal to phi a sfy d minus a by 2. And when depth of the beam increases, area of steel will decrease. And you know that concrete is cheaper than steel. So if we slightly increase depth, it has a lot of advantages. One of the advantages that the reinforcement required will be less. The other is that the deflection will be controlled very well, because the L by 16 equation gives us a minimum depth according to the ACI code. So if we assume slightly greater depth than this, then it will further improve the performance of the beam in the deflection control. So these are the advantages of them. However, it is also to be understood that a deep beam, a beam which is very deep, so a beam which is very deep will also have some problems or disadvantages. One of the disadvantages will be that it will increase the weight of the beam, unnecessarily increase the weight of the beam. And it may not reduce the area of steel because there is a minimum reinforcement requirement. So regardless of your size, you will always have to place that minimum reinforcement inside the beam. So the depth of the beam shall be within the reasonable limits. These things you will understand slowly and gradually when you solve several problems. You come across different situations, so then you will understand what are the reasonable depths. The depths which are currently used, and the depths which we are using currently in the market in our projects are around 15-inch wide, 21-inch deep, 15, 20, or instead of 21-inch, 24-inch deep. 15-inch wide and 24-inch deep is our typical beam that we use these days in our projects. 15-inch wide and 24-inch deep. This is our typical beam that we are using in the projects nowadays. Okay, the depth, there is no criteria for the minimum depth by the ACI code, but usually depths less than 12-inch are not used in the market, because if a beam is very narrow, then the number of bars to be placed inside the beam will become very difficult, and the reinforcement will be very congested, and it will be difficult for concrete to flow around all these bars, and perfect bonding between steel and concrete will not be achieved, which will prevent the flexure capacity of the beam to be fully developed. Okay. Okay, then we say that generally the minimum depth of the beam is 12 inch, therefore width of beam is taken as 12 inch. So 12 inch, 15 inch, these are generally the width of the beam, 12 inch and 15 inch. But for a very long span beam, the width can be 18 inch also, 18 inch or even more than this. The final selection of beam size depends on several factors, especially the availability of formwork. So we have selected a beam which is 18 inch deep and 12 inch wide. And initially, we will assume some effective depth of the beam. We know that H is equal to D plus Y bar. Y bar is the distance from the bottom of the beam to the centroid of the reinforcement. And Y bar is usually, you should remember that you should take this from 2.5 to 3 inch. Okay? So if Y bar is taken at 2.5 inch, then D is equal to 18 minus 2.5 equal to 15.5 inch. If you take this 3 inches, this will become how much? Y bar will become equal to, D is equal to 18 minus, if Y bar is 3 inch, then D will be equal to 18 minus 3. This will become 15 inch. So effective D will depend on the assumption of Y bar. Y bar can be 2.5, can be 2.75 or 3 inches. Because generally the reinforcement will be placed at such a distance from the bottom that it will, that Y bar will range from 2.5 to 3 inch. In the reinforced concrete course, the width of the beam is usually denoted by BW instead of B. So in our calculations and in our next slide, we will use B with subscript W, which means web width W. This is the web, but you will see in the next slides. So this will be the width of the beam will be denoted by B with subscript W. So we have selected the width of the beam and depth of the beam. Depth is 18 inch, width is 12 inch, and effective D is 15.5 inch because we assumed Y bar equal to 2.5. How is this assumption made? I will explain this. How is this assumption made? You know that we have said in our previous lecture that for the protection of reinforcement from corrosion, at least 1.5 inch clear cover of concrete shall be provided on all sides of the beam. So 1.5 inch will be clear cover. Then this stirrup will always be there because we will be needing the stirrup to strengthen the beam against shear forces. So this will be, and normally the size of this reinforced this stirrup is 3 by 8 inch, 3 by 8 inch diameter, 3 by 8 inch diameter. Number 3 bar, which means the diameter of this bar is 3 by 8 inch. And then let's say this bar can be assumed. Generally, what are the bar diameter that we use in our beam design? Mostly number 6 bar is used in beams, mostly. But we can also use number 4 bar, number 5 bar, number 6 bar, number 7 bar, number 8 bar. Okay, then again, the availability of these bars in the market can become challenging at times. But the readily available bars in the market are number 4 bar, number 6 bar, and number 8 bar. These are readily available in the market. They are always available even in a local market. But other bars are also available in big cities from number 8 to number 4 bars. Okay, so let's say we use a number 6 bar here. So this will be 1.5 inch plus 3 by 8 inch, and then 6 by 8, which is 3 by 4, and half of 3 by 4. So this will be equal to how much? You should calculate this. If this bar diameter is 3 by 4 inch, then what should be Y bar equal to? You calculate it yourself and tell me.
$2.25.
2.25. Okay. So when Y bar is 2.25, then how much shall be D? D shall be equal to H minus Y bar. H is equal to how much? 18 inch?
15.7.
G.
15.75.
15.75 inch. Okay. So in the beginning, we can assume any diameter of the bar, and it will give us Y bar. Let's say if we assume that the bar is 1 inch in the beginning. So now it will be number 8 bar. And in case of number 8 bar, it will be 1.5 plus 3 by 8 plus 0.5 inch.
$2.375.
2.375. And D will be
15.625.
15.61. And if you look at this assumption that we have made, we have taken y bar equal to 2.5 inch. And D is equal to 18 minus 2.5 is 15.5 inch. So this may not correspond to any specific size of the bar that we are assuming. We can just assume y bar of any length from 2.5 to 3 inches. Any distance from 2.5 to 3 inches. Okay. And then finally, we will see what is the effect of this change in D. This was the first step on the selection of sizes. Second step is loads. So we should calculate the self-weight of the beam, because self-weight of the beam is, if you remember from the statement of the design example, self-weight of the beam is not included in the dead weight of the beam. Self-weight of the beam can be very easily calculated like this. You know that the section of the beam is 12 by 18 inch. So a beam we will calculate and 0.15 is the density of beam. 0.15 kip per cubic foot is the density of beam. So 12 by 18 divided by 144, this will give us 0.225 kip per foot weight of the beam per foot for each foot of the beam. So this will be uniformly distributed load. This is again a uniformly distributed load per foot, which means 225 pound per foot. What is the normal weight of a person? Normal weight of a person?
60 to 70 kilogram.
Pound?
Kilogram.
In pounds. We are talking about pounds.
130.
Let's say 150. So 150 pound is the weight of one person, and this beam has a weight of 225 pound per foot. So every foot of this beam has a weight of 225 pound, which is greater than the weight of a normal person. You can see. So by comparing the weight of a normal person, you can at least realize what a 225 pound weight means. You can at least realize that 225 pound is a lot of weight, 225 pound, and every foot of the beam. So this is the self-weight of the beam. This is the self-weight of the beam without any additional weight on the beam. So in reinforced concrete members have a self-weight, substantial part of the weight is self-weight. Substantial part of the total weight is self-weight of the beam, because the sections that we use are very thick. Unlike steel structures, where the sections are very thin. Okay, then we will assume this equation of the load combination, where the ultimate load is calculated by addition of the factor dead load and factor live load. The dead load that we have calculated right now is 2.225 foot, but the weight that is given to us in the design example is 0.5. From where does this 0.5 kip per foot weight come? This you will learn, but this may be some kind of flooring because this will be fixed weight. This weight, which which we call a superimposed dead load, superimposed SDL. We call this SDL, superimposed dead load. Why superimposed dead load? Because this dead load is this load is over and above the self weight of the structure. Dead load also contains self weight of the structure, which is 0.2255 in this case. And superimposed dead load is dead load over and above the self weight, or dead load in addition to the self weight. So 0.5 is superimposed dead load, which can come from many sources. Let's say, for example, marble flooring is done in a room, and let's say a wall is constructed on top of a beam. Okay, so the weight of the wall will be superimposed dead load on the beam. On the beam, it will be superimposed dead load. Okay, because the dead load of the beam itself is dead load, but any other load which stays there for a long time will be called a superimposed dead load. So if a wall is constructed on top of a beam, this will not be live load. This will be superimposed dead load on the beam. Okay, and live load can come, for example, from in the case of a school or college, the weight of the students will be live load. Okay, in the case of stores, the weight of all the things that are to be kept inside the room will be live load, because the position of the commodities kept in the room will change. They may change from time to time. So any load which changes in space and time will be called as live load. Live load will change. So 0.5 kip per foot, which is 500 pound per foot, 500 pound. So the weight is equal to 500 pound weight is equal to how many person? If the weight of one person is 150, so it is more than 3 persons. Every foot of this beam is taking a load of 500 pound live load, and also 500 pound superimposed dead load. So this is a lot of weight. And then we are amplifying these weights, and finally the weight comes out to 1.67 kip per foot. 1.67 kip per foot is 1670 pound per foot. This weight is equal to how many persons? (1670) divided by 150.
Almost 13%. Almost 13%.
12 almost.
12, around 12.
12. And 12 persons standing on 1 foot. Okay? 12 persons, not on the whole beam. 1 foot of the beam. 1 foot of the beam, 12 persons. If 12 persons are standing within an area of 1 foot on the beam, then that will be equal to 1670 pound, because this is 1 foot of the beam. For the total weight of the beam, 1670 shall be multiplied with 20, because the total length of the beam is 20. 1670 into 20. This will be the whole weight that this beam will be carrying. Okay. So this is a lot of weight. You can see, you can realize that a lot of weight is to be carried by this beam. Next is the analysis. We will only talk about the bending moment at this time, although we have drawn the shear force diagram, because this is simply supported beam. You can try this. I will give you just 5 to 10 minutes, and you can try drawing shear force and bending moment diagram for this beam, which is simply supported and has a weight of 1.67 kip per foot. You can draw this yourself, shear force and bending moment diagram. Okay? Take your time and draw shear force bending moment diagram yourself for this beam, which is 20 feet long. The beam is 20 feet long. Okay. So have you calculated the bend moment and show force diagram? This is for the simple beam.
Yes, sir.
Yes, sir.
Okay. 1.67 into 10 will give you reaction on one side, and 1.67 into 10 will give you the reaction on the other side. So you can draw shear force diagram with this, and half of this area, triangular area, if you calculate this, it will give you the bend moment diagram 16.7 into 10 divided by 2. This will give you bend moment 1002 inch cape. Okay, I know you can draw bend moment shear force diagram very quickly for such beams. Now the next step is design step, and in the design step, the basic thing that we have been discussing from the beginning, that the flexure capacity, which is now 5 mn. The design, it is called the design. Mn is what? Mn is nominal capacity. Mn alone is nominal capacity. When Mn is multiplied by 5, this becomes design capacity, because we are slightly reducing this for the purpose of introducing safety in our designs. So 5 Mn is Md. This design capacity shall be greater than or equal to Mu. Mu is applied demand. So 5 Mn is our design capacity. This shall be greater than or equal to the applied ultimate bending moment, which comes from the load and the length. We have seen that this comes from the load and the length. This is the applied bending moment, which the beam has to resist. And this is the resistance offered by the beam. The resistance offered by the beam must be greater than the applied demand. This resistance is now the flexure resistance or flexure capacity. 5 Mn is flexure capacity or bending capacity. 5 Mn is flexural or bending capacity, but design capacity. And Mn is nominal flexure capacity. Mn is nominal flexure capacity. 5 Mn is design flexure capacity. This is not capacity. On the right side, Mu is not capacity. Mu is the applied moment, which comes from the load and from the length of the beam. This is the demand on the beam, which the beam must have to carry. If the beam is not to fail, then 5 Mn must be greater than or equal. But at least 5 Mn shall be equal to Mu in order to make the beam such that it carries this demand of Mu without failure. This is the basic requirement, that 5 Mn must be at least equal to Mu. Okay, for no failure. When this 5 Mn is equal to Mu, then 5 As Fyd minus A by 2 shall be equal to Mu, and from this we will calculate As. As is equal to Mu divided by 5 Fyd minus A by 2. We will calculate As by trial and success method. Because in the beginning we do not know small a. Small a will assume. We will calculate As, then we will calculate small a by this equation, As Fy divided by 0.85 Fc prime B, which you will see in the next slides. First trial is that, let's say we assume small a, and I will ask you now to do this calculation yourself. Okay, we will today we will go very slowly so that you can calculate. You can do calculations in all these steps yourself, so that you become familiar with these calculations. Okay, so today we will go very slowly, and I will ask you now that by assuming small a equal to 0.2, although you can assume any depth of small a, but this will give you a very good head start if you do this from 0.2d. Small a is equal to 0.2d. You know d was 15.5, so this will be 0.2 into 15.5. This is the initial assumption that you will make. So small a is equal to 3.1 inches. Then you calculate As, because this is Mu, 0.9 Fy, d you have assumed this is A, 3.1 divided by 2. So As is calculated like this. Then calculate small a from this As. From this As that you have calculated in this step, this substituted here. And calculate small a. And after this small a is calculated, recalculate As by substituting small a in this equation. I would ask you now to do this and tell me the final value of As. Final value of As. The final value of As will be that value which will not change okay, which will no longer change after you do trials. So the value that does not change from the previous value, then that will be the final value. Okay, so you do your trials and tell me what is your final value of AS. I will give you now 10 minutes. In these 10 minutes, you should try. And also, if you could calculate AS max and AS minimum, I will appreciate. Calculate AS and also calculate AS max and AS minimum. And this should be done in 10 minutes. You can discuss it among yourself if you want. Okay, and after 10 minutes, then we will go ahead with this example. To complete this example, we will do the other steps like the placement of reinforcement. After you calculate AS and AS, tell me what is the value of AS, AS max, and AS minimum. Please do this and tell me the values. Do trials, take your time, discuss it among yourselves, and tell me three things. The value of, final value of AS, AS max, and AS minimum. And also check whether AS calculated is between AS max or between AS max and AS minimum or not. Okay, please do this. Any one of you who has completed the calculation?
Yes, sir.
Please, what is the final value of AS?
Sir, 1.9573.
1.9573. Okay, I will write this. What is AS max? Have you calculated AS max, maximum area of steel?
Yes, sir. Yes, sir. 4.2 and AS minimum is 0.93 and 0.744, but we take the maximum of it, so it is 0.93 in square.
Okay, very good. What is your name?
Qaim Shah.
Qaim Shah. Okay, good. Okay, we will see now your values, whether they are correct or not. So after the second trial, the AS comes out to be 1.96. In third trial, the value comes out to be 1.95. We have not taken the two more digits, 1.9573, because you will see now when we will be trying to calculate the number of bars, that this 2 digits will be more than enough, because finally we will be making a lot of approximations, okay, as you will see in the next slides. Now, AS minimum and max, minimum reinforcement is 0.93 square inch, so this is correct. AS maximum is 4.2 square inch, this is also correct. AS max, once again, you can see that this is 0.3 FC prime divided by Fy BWD. 0.3 into 3 by 40 into 12 into 15.5 is 4.2 square inch, okay. AS minimum is from this equation, as you said that from one equation it comes out to be 0.744, and from the other it comes out to be 0.93. And if you remember last time I told you that there is no need to check this equation 3 FC prime Fy BWD, because the other equation 200 divided by Fy BWD will always give you value greater than this value, as long as FC prime is not more than 4500 psi. Okay, as long as FC prime is not greater than 4500 psi, the second equation 200 divided by Fy BWD will always give you the greater value than this equation. Because if you substitute the value of 4500 psi in this equation, this 3 into 4500 psi, square root of 4500 psi will become equal to almost 200. And any value of C prime greater than 4500 psi will give you 3 times the square root of the prime value greater than this 200. And the rest of the equation is same. 3 FC prime, 3 into square root of C prime, and 200. These are different. Otherwise, Fy BWDs are same. So you should remember these things. Okay, now finally, the value which we have calculated is AS 1.95 square inch, and this shall be less than AS max and more than AS minimum. Okay, what should we do? This is another question from all of you. If AS that we calculate from this step comes out to be less than AS minimum, what should we do? If calculated AS comes out to be less than AS minimum, then what should be our next step?
Sir, we can change the reinforcement grade. Instead 40, we use 60 grade.
Who are you? What is your name?
Shah Khalid.
Shah Khalid. Now, if AS comes out to be less than AS minimum, there is no need to change the grade of steel. We will have to use this AS minimum instead of this AS. Let's say this AS comes out to be 0.6 square inch. Okay, you should pay attention to this now. If this AS, calculated AS comes out to be 0.6, for example, then 0.6 will be less than 0.93. In that case, we will use 0.93 instead of 0.6, because minimum area of steel we must have to use in our reinforced concrete beam. This is the minimum reinforcement. The reinforcement that you want to use in a reinforced concrete beam cannot be less than AS minimum in any case. Okay. So whatever the dimensions of the beam are, AS minimum shall be calculated according to their dimension based on the ACI code equations, and the AS minimum which comes out to be which is calculated from these two equations and the greater value is selected, that AS minimum shall always be used in the beam. Okay, regardless of what is your final value of AS calculated. Okay, I hope this is clear now.
Yes, sir.
Okay, so minimum area of steel is the minimum area that must be used in reinforced concrete beam, and this will change with the size of the beam. You know this now because it depends on B and D. Is this clear to all of you? That if AS is calculated and AS from the trials and success method, if AS comes out to be less than AS minimum, then we will use AS minimum. Okay. The next
Yes.
question is, can you tell me a condition where there is a greater chance of AS to be less than AS minimum? Can you think of a situation? Can you think of a situation where AS comes out to be less than AS minimum? Why would it happen? देखिए AS की वैल्यू किस चीज पे डिपेंड करती है? AS डिपेंड्स ऑन द वैल्यू ऑफ AS. यू कैलकुलेट AS फ्रॉम दिस इक्वेशन mu divided by 0.9 Fy d minus A by 2. So if mu is less, which is demand, then AS will be less if mu is less. Correct? If mu is less, then AS will be less, which is demand. So if load on the beam is less or length of the beam is less, then mu will be less and AS will be less. Similarly, if beam is very deep, d minus A by 2 is in the denominator. So a deeper beam will give you less S. Okay, a deeper beam can give you less S. Similarly, the grade of steel, the greater value of Fy can also give you small AS. So if load is very, very small or if beam is very, very deep, then AS can be less than AS minimum. It's possible. But if that is the case, then AS minimum shall be used and not this AS. Okay? Okay, this was regarding the AS. When if AS is more than AS max, then what should we do? If AS comes out to be more than AS max, what should we do? Because it is not allowed to use AS more than AS max. What should we do if AS comes out to be more than AS max?
Take AS max.
जी?
Take the AS max as the condition.
दोबारा बोलें आप. ये मैं कह रहा हूं कि अगर AS की वैल्यू जो हमने कैलकुलेट की है 1.95, लेट्स से दिस वैल्यू कम्स आउट टू बी 4.5 स्क्वायर इंच, तो फिर AS की वैल्यू AS मैक्सिमम से बढ़ जाएगी. उसमें हमें क्या करना पड़ेगा फिर? What should we do then?
सर 4.2 ले लेंगे.
4.2 नहीं, तो आपको रिक्वायर तो 4.5 है, तो 4.2 कैसे लेंगे? रिक्वायर तो 4.5 है ना. ये आपने 4.5 तो इक्वेशन से मालूम की है कि इतनी रिइंफोर्समेंट आपको चाहिए कि आपका बीम फेल ना हो, तो आप उसको कम कैसे कर सकते? अपनी मर्जी से तो कम नहीं कर सकते. You can't do anything with this AS. आपने क्या करना है? अगर आप AS की इक्वेशन को देखें तो AS मैं दोबारा लिखता हूं mu divided by 0.9 fy and d minus a by 2. तो आप इससे as मालूम करते हैं ना. mu तो आप चेंज नहीं कर सकते, चेंज कर सकते हैं because load will come from a demand. You can't do this always. This is not in your control. This will come from the demand, from a situation, a requirement. A beam is so long and so load, so this you can't do anything with this. Okay. Maybe you are also not able to do anything with fy. So you can increase
डेप्थ को ज्यादा
जी
बीम की डेप्थ को ज्यादा करेंगे.
बीम की डेप्थ को ज्यादा करेंगे. यस, जब बीम की डेप्थ को आप ज्यादा करेंगे तो एस आपका कम हो जाएगा. ठीक है ना. आप खामखा एस को कम नहीं कर सकते अपनी मर्जी से. आपने बीम के साइज को देखें. the flexure capacity, the basic equation for the flexure capacity is this phi mn. If you pay attention to this, this is phi as fy d minus a by 2. This is flexure capacity of the beam. The flexure capacity of the beam is composed of two things. Two things are giving the flexure capacity of the beam. One is the material strength, and the other is the size of the beam. What is the strength of material? The strength of material is this thing, Fy. Okay, AS is not the material strength. AS is the area. This is the size. Fy is the strength. So strength is here. And then the size of the material, the size of the beam. The size of the beam is d minus a by 2, but the size is also AS because this is the size of the steel, area of steel. So either by increasing area of steel or strength of the steel or size of the beam, you can increase the flexure capacity of the beam. Okay, so the capacity comes from two things. One is the size of the section, in this case size of the beam, which is B and D, but phi mn is directly proportional to D. So instead of increasing B, if you increase D, it will have a lot of effect on phi mn. And the other is strength Fy. Fy, the maximum strength that we can have in Pakistan is 60 KSI. So Fy is 60. And AS can also be increased if you increase AS, but AS cannot be more than AS max as per ACI code. Okay, so in that case, you will have to increase the depth of the beam. There will be situations where the depth of the beam, changing the depth of the beam may not be possible for certain reasons, but that we will discuss some other time. That what can we do if we cannot change the depth of the beam and still to satisfy the ACI code criteria, that AS shall be less than AS max. This we can do, but this we will discuss some other time. Okay, so with this now we go ahead. Finally, now we will need some bars to be placed inside this beam. For this, we will have to select a particular bar size. Okay, you can select any bar size, but you have to keep in mind certain things. There should not be too many bars to be placed. If the bars are too many, then the bars will be too congested inside the beam, and it will prevent the flow of concrete around the bars. So the condition of reinforcement shall be avoided. For this purpose, too small a bar diameter shall not be placed inside the bar, keeping in view your area of steel required. In this case, our area of steel required is 4 number 7 bar. So just to start with, let's say we are using number 4 bar. So can you calculate now? Can you calculate the number of bars for 1.95 square inch? 1.95 square inch is the area of steel required. Try number 4, number 5, number 6, number 7, number 8 bar and tell me the number of bars required. Okay, prepare a table. Area of steel required is 1.95. If you use number 4 bar, how many bars are to be placed? If you use number 5 bar, how many bars are to be placed? Please calculate this and tell me. How many bars are to be placed in the case of number 4, number 5, number 6, number 7, number 8 bars? Okay, how many bars are required if you use number 4 bar?
Sir, 4.
What is the area of steel of number 4 bar?
4 by 8.
What is the area of steel of number 4 bar? Do you remember the
Sir,
area?
0.2 square inch.
1.95 is the total area of steel required. So divide 1.95 by 0.2.
Sir, 9.75 तो approximately 10 bars.
10 bars हमें डालने पड़ेंगे ना. अच्छा, अब नंबर 5 बार ट्राई करें. नंबर 5 बार एरिया ऑफ स्टील फॉर नंबर 5 बार इज 0.3 स्क्वायर इंच.
Sir, almost 6 bars, sir.
ऑलमोस्ट 6 नहीं है.
7 sir,
1.95
7.
7 बार आप डालेंगे. आप कम तो नहीं डाल सकते. एरिया ऑफ स्टील आप कम हो जाएगा.
Yes, sir.
अच्छा, अब नंबर 6 बार ट्राई करें. नंबर 6 बार एरिया ऑफ स्टील कितना है?
Sir, 5 bars, number of bars. और area है 0.44 square inch.
0.44. 1.95 divided by 0.44 will give you 4.43 bars, which means 5 bars. Okay, आप नंबर 7 बार करें. नंबर 7 बार का एरिया ऑफ स्टील कितना है? नंबर 7 बार का 0.6 स्क्वायर इंच.
0.6 जी सर, 4 bars आ गई 3.25.
अब नंबर 8 ट्राई करें.
Sir,
3 bars.
3 बार. ओके.
2.46.
तो अब आप मुझे बताएं which bars we should finally use. If you use number 4 bar, you can see that 10 bars will be required. And the width of the beam is 12 inch. Okay. So if you try using number 4 bar, you will probably require 2 layers of reinforcement or 3 layers of reinforcement. Because, okay, let's say, let me demonstrate this to you. So because this is your first problem, we will learn how we select the bar to be placed inside the beam. Okay, this is the stirrup, and this is the available space. This is the available space. Let's say the beam is having a width of 12 inch. Okay, so 3 inch, 1.5 inch, 1.5. The available space for the bars. 12 inch minus 1.5 minus 1.5 minus 3 by 8 on one side, minus 3 by 8 on the other side. This will become 3 by 8 multiplied by 2. So what is the available space now? The available space, 12 minus 3 minus 3 by 4.
8.25.
The available space is 8.25.
25.
Okay, this is the available space. Okay, and the diameter of the bar in the case of number 4 is ½ inch. Okay, excuse me, just give me. the end of this week. Confirm, yes, confirm. Taking of the Qaiser class. Qaiser class, I tried to explain to you initially, it is the problem of settlement from the what is the Qaiser from the what is the type Qaiser identified. So until this we rectify this process of the most because the team, our team, which were part of this earliest site, they couldn't be the problem with almost all the practice class. In being it better now. Yeah. But if the foundation, if the foundation is setting, it's not going to work. The water is seeking. The water is seeking to the foundation. Foundation is the soil, it will be deep soft. So, yeah, so the water is not soft. Because the base was already Because that is our rights in rights, our job rights in what comes here, we have to go from the but the repair of the wall, I think it should be done after the that's what the joke is that's a great directive water. What creation of those. Our concept of giving the certificate of stability of married class, this married class will not put in place because they will not be eligible for it, unlike the class ones. This is very good. I think you test this. Okay, so the available space is 8.25 inch. Okay, and the diameter of
Excuse
number
me,
4
sir.
bar is half. Please.
Sir, can you please explain again the space?
मैं आपका सवाल नहीं सुन सका सही, बताइए दोबारा.
Sir, can you once again explain the available space?
Available space, yes, I explain. The width of the total width of the beam is 12 inch. Okay. Okay.
Yes, sir. Yes, sir. I'm listening.
Okay. Then we have a strip inside this, which will always be there. in order to resist the shear forces. So the diameter of this ring is normally 3 by 8 inch. The diameter is 3 by 8 inch. The clear cover from both sides will be 1.5 inch. So we are calculated now this available space. This is the available space inside this stirrup. So if the total width is 12 inch, 1.5 inch from one side and 1.5 inch on the other side will be deducted, because you cannot place reinforcement inside this space. And then you have 3 by 8 inch stirrup on one side and 3 by 8 inch stirrup on the other side. So this is minus 3 by 8 into 2. This is minus 0.75. So the available space is 12 minus 1.5 minus 1.5 minus this, which is 8.25 inch. 8.25 inch. Okay?
Yes, sir. Yes, sir. Thank you, sir.
Available space is 8.25 inch. Now we have to place bars within this space. Within this space. If we are using number 4 bar, then we would just calculated that 10 bars will be required. 10 bars. If bar is number 4. In the case of number 4, 10 bars are required. Now, and we have available space equal to 8.25 inch. The diameter of one bar is of number 4 is half inch. D is equal to 0.5 inch. 0.5 into 10. So we need a 5 inch space. But between the bars, you must have to have some space. If you place one bar here and one bar here, okay, and then we can place other bars at least 1.5 inch apart, clear, 1.5 inch, 1.5 inch from one bar to another bar. Spacing 1.5 inch. Okay, so half inch plus 1.5 inch is how much? 2 inch, and then another 0.5 inch, 3 inch, and then a space of 1.5 inch again. So there will be 3 spaces of 1.5, 1.5. 1.5 multiplied by 3 will be 4.5 inch. And then 1, 2, 3, 4. This will be 2 inch because this is diameter is 0.5 inch. So 4 multiplied by 0.5 will be 2 inch. So 6.5 inch. So you still have some space to place at least one more bar. If you place one more bar, there will be a space of 1.5 inch additional and 0.5. So 2. So 0.5 plus 1.5, 6.5 is 8 inch. So 8 inch space is consumed by placing 5 bars. If 5 bars of number 4 are placed in one layer, then this total space of 8.25 inch will be consumed. Then the remaining 3 bars will be placed on top of this in another layer, remaining in another layer. Okay, 5 and 3 more bars. This will be the situation for number 4 bar. If we try number 5 bars, number 6 bar, number 7 bar, if you remember, I showed to you one of the table. If you remember, I will show the table once again. This is the table. This is the table for a maximum number of bars we place in one layer. These are the bar number 5, 6, 7, 8. Although number 4 bar is not included in this, number 5, 6, 7, 8. The beam width is 12 inch. So if we are using number 5 bar, the maximum number of bar that can be placed in one layer are 5. We have just recently, seen this, that if you use number 4 bar, maximum number of bars which can be placed in one layer are 5 bars. Similarly, for number 5 bar also, these bars comes out to be 5 bars in one layer. The remaining bars will be placed in another layer. For number 6 bar, the maximum number of bars that can be placed in 12 inch wide beam are 4, and we need 5 bars we need 5 bars. So which means that 4 bars can be placed in one layer, and one bar is remaining, which may be placed in another layer. But according to the ACI code, 1 bar cannot be placed in another layer. So we will place 3 bars in one layer and 2 bars in another layer. This kind of adjustment we will have to do in the final placement of bar. This becomes very difficult for the beginner. For learner like you, this will become a challenge for you to place the number of bars, but slowly and gradually you will learn these things. Okay, so if we decide 5 number 6 bar, which will provide us 2.2 square inch instead of 1.95 square inch, which is slightly greater than required. Okay, we can place these 5 number 6 bars. Other options, 4 number 7 bar, you have calculated this, or 3 number 8 bar. We can also use combination of 2 different diameter bars, but keeping in view that in one layer, the difference shall not be more than 2 sizes. Finally, we decide to place our bars like this, 3 plus 2. Although we can place 4 bars in one layer and 1 bar which is remaining, but that 1 bar cannot be placed in the second layer. So for this purpose, instead of placing 4 bars in one layer, we place 3 bars in one layer and 2 bars in another layer, and the adjustment is made like this. These 2 bars, why these 2 bars are placed, this we will discuss some other time. At the moment, we are concentrating now on these bottom bars, which are 3 plus 2 bars, and they are placed in this manner. I hope this is clear. If you have any question on this, please ask your question.
Sir, 1.
Yeah, please.
हम साइड से 1.5 स्पेस क्यों देते हैं सर?
जी
सर हम बार्स को रखते वक्त 1.5 स्पेस क्यों देते हैं सर साइड से?
क्यों देते हैं?
यस सर।
वो कवर देते हैं, कम मिनिमम कवर, ताकि स्टील रस्टिंग न करे ना, स्टील को जंग लग जाता है, इट करोड्स if protection is not given to steel from site. ठीक है? Okay?
Yes sir.
Okay, now in the beginning we assumed effective depth equal to how much? Remember what was the effective depth that we assumed in the beginning of the problem? It was 15.5 inch. Okay, in the beginning we assumed effective depth D was initially assumed as 15.5 inch. Now after we have placed this reinforcement, we exactly know the effective depth now, and we can calculate this very easily. We have now this reinforcement 3 plus 2 bars. So just like the previous explanation of calculating y bar, the same repetition of that calculation of y bar. Total 5 bars are there. 5 multiplied by 0.44, because the area of one bar is 0.44, and then multiplied by y bar, 5 into 0.44 into y bar, equal to 3 bars in one layer, multiply by 0.44 into y1, plus 2 bars into 0.44 into y2. y1 and y2 are known, because 1.5 inch is the clear cover, 3 by 8 inch plus half of the diameter of 3 by 4 inch bar. So y1 and y2 are, y bar comes out to be 3.15 inch in this case now. And the D, effective D, which was assumed in the beginning 15.5 inch, now actually it comes out to be 14.85 inch. Since this actual D is less than the assumed D, so it will slightly reduce phi mn. But since we have area of steel slightly more than the required area of steel was 1.95. And because of the adjustment in the number of bars, the area of steel comes out to 2.2 square inch, 5 into 0.4. So this is the actual area of steel, and this is actual D now. Okay, so we can calculate small a from this AS now, small a, because this is the actual area of steel. So we can calculate actual A now, ASFY 0.85 C prime BW from this actual area of steel. A comes out to be 2.87 inch. And now with this small a and this d, we can exactly calculate the phi mn, which will be given to us by this reinforcement. So phi as is 0.9, as is 2.2, fy is 14 now, d is 14.85, and actual a, which comes out from this area of shield, so this is 1062.5 inch cap. Still the phi mn is greater than 1002 inch cap. Why? Because the area of steel required was 1.95, and the area of steel that we have provided is 2.2. Although d comes out to be less than the assumed d, but the area of steel that we have provided is more than the as required. So phi mn finally comes out to be more than mu, so this is okay. If this is not the case, then we have to slightly increase as and recalculate small a and repeat our design problem calculation. Okay. Finally, the drafting phase. The drafting phase, you can see the beam length in 3-dimensional is given, shown to you, and there are 3 bars, 3 plus 2 bars here. There is a spacer bar given. The spacer bar will be necessary because these 3 bars are easily supported on the stirrup here. They need a support, but these 2 bars will need a support. Either these 2 bars can be tied with this 3/8 inch stirrup on this side, or a spacer bar can be provided. Spacer bar, which will make sure that a space of 1.5 inch is kept between these 2 bars. The spacer bar will not be provided at every location. If you are able to see the spacer bar here, they are shown here. So one spacer bar is here, one spacer bar is here. These spacer bars are provided because the 2 bars which will be placed in the second layer need the support. So this support is provided by these spacer bars here. Okay. Next, I will show you a video where you will be able to see actually the reinforcement in detail. You pay attention to the video and look at the reinforcement which is being placed. The bars have been carried to the far end of the support, to this point, 3 bars, and then the 2 bars have been curtailed. You can see these 2 bars, they're not carried to the support. I will explain the reason for this. These are the spacer bars. Spacer bars are also visible. Okay, this was 3D view of this.
सर स्पेसर बार की जगह हम वायर यूज कर सकते हैं?
ये वायर यूज कर सकते हैं 2 बार अगर आपके पास हो ना, जिस तरह की ये केस है। लेकिन अगर 3 बार हो तो फिर वायर फायदा नहीं देगा, क्योंकि वो दरमियान में आ जाएगा ना, तो उसके लिए फिर आपको स्पेसर बार की जरूरत पड़ेगी। अगर सेकंड लेयर में 3 बार हो, दरमियान वाले बार को सपोर्ट चाहिए फिर। ओके
ओके सर।
ओके, ये 2 बार हमने काट दिए हैं। व्हाट इज द रीजन फॉर दिस? बिकॉज वी हैव कैलकुलेटेड दीज 5 बार्स बेस्ड ऑन द मैक्सिमम बेंडिंग मोमेंट। ठीक है ना? अगर आपको बेंडिंग मोमेंट डायग्राम में इस पे ड्रा कर दूं, तो बेंडिंग मोमेंट डायग्राम की शक्ल हमारी इस तरह से है। आप देख सकते हैं कि इस जगह के इस बेंडिंग मोमेंट के लिए मैंने ये कैलकुलेशन की है, लेकिन अगर मैं देखूं तो इस जगह पर ये बेंडिंग मोमेंट काफी कम है कि नहीं? अगर मैं इस एमयू को इस्तेमाल करूं और इस पे मैं एरिया ऑफ शील्ड निकालूं तो वो काफी कम एरिया ऑफ शील्ड रिक्वायर्ड होगा, इजंट इट? ऐसे होगा कि नहीं? दिस एमयू वाज 1002. This MU will not be 1000. This may be 300 or whatever it is. You can calculate this from the distance of the support. So instead of carrying these 2 bars to the support, we can curtail these 2 bars here, and we can curtail these 2 bars here at this location, okay, where they are no longer required, and to save some money, okay. So this is called curtailment of reinforcement. This we will discuss in some other lecture, but at the moment you can see that all these 5 bars are not carried to the support. The 2 bars in the second layer have been curtailed at some distance where they are no longer required, because the number of bars, the area of steel required was calculated based on this maximum M, which is only in this region, okay. But after that, the bending moment decreases until it becomes 0 at the support. So very close to support, the bending moment value will be very small. So to save some money, we can curtail few bars. These are some recommendation of the ACI code. We must have to follow this recommendation. For example, the ACI code says that 1/3 of the total bar shall always be carried to support. But I would recommend to you that 50% of the bars shall be carried to support. In this case, these are 5 bars. So 3 bars have been carried to support, which means 67% of the bars have been carried to support, and 33% have been curtailed, which is allowed as per ACI code. And this distance can be calculated. I will explain to you this thing some other time. But at the moment, the design is over now, and you have successfully designed your first beam. Okay, I will give you some home assignments. This is not a typical home assignment that you get and you have to submit, but this is a class activity. You can design a reinforced concrete simply supported beam having a span length of 30 feet and supporting a service dead load of 1.5 kip per foot and uniform service light load of 1.1 kip per foot in addition to its self-weight, FC prime and FY. Now you can practice this. Okay, give me a break for 15 minutes or pray, and you can practice this yourself now, right now in the class. And after the break, 15 minutes, if you have any question, we can discuss this. You can take help from the previous example. Okay, take a start from the beginning by selecting appropriate size of the beam, and then calculate loads, and then analyze the beam. It is simply supported, so the analysis is not difficult. And then start designing this. Okay, follow the steps of the design example that we have just finished. Okay, and after 15 minutes, we will discuss any problem that you are facing. Okay, in the design problem. So you start this, please start this. You can discuss it among yourselves. Okay, start designing this beam. The beam length is 30 feet this time. The loads are different slightly, and the FC prime and FY wheels are also different. But anyway, the procedure will be the same. You can exactly follow the same procedure and design this beam yourself in the class. Okay, after 15 minutes, then I will give you time for questions. Okay. You can try this in 15 minutes, please. Okay, do you have any questions? Any question? Okay, I advise that you practice this example and then come up with your question next time. Okay?
Okay, sir.
Okay. So this is the end of today's lecture. Thank you. Khuda Hafiz. Assalamu alaikum.
Allah.